there. Here
we give the supply, 3-phase balanced supply, we give it to the stator. Then after, we give the excitation to the rotor to make the rotation synchronized. Rotor field and stator rotating magnetic field should lock each other, and that synchronous speed it will rotate. It has specific applications, particularly in power systems. So effect of over-excitation in case of alternators, as we discussed, that is purely demagnetizing, right? And it is giving lagging power factor, or otherwise reactive power into the system. We discussed this in the parallel operation of alternators and with the infinite bus bar, how the synchronizing power upon over-excitation condition, it is delivering reactive power. Similarly, vice versa. Synchronous motors, particularly, since the operation is Fleming's right hand rule and Fleming's left hand rule. Rule is same, but analog, the similarity just quietly differs from the alternators. Here, industrial at the power system applications, it is to supply the leading power factor. Usually, then for that application, it is known as synchronous condenser, right? Power factor correction purpose, one basic application of this synchronous motor is for one constant machine drives, irrespective of the load. If we want to keep the speed of the machine, usually these are the motors nowadays we are employing in the EV vehicles. Right, permanent magnet, earlier BLDC motors, nowadays people are now working in PMS, permanent magnet synchronous motors. We have synchronous reluctance motors are also synchronous reluctance motor. Those are special purpose motors which are exclusively now research is running on that particular area. So synchronous motor has its own advantages. So this V curve and inverted V curve, what it is giving, if you observe, V curve is that curve drawn between excitation and field current. Field current, where are we giving field current here? To? No. Excitation giving to what? Where are we giving excitation in a synchronous motor? Rotor. Field winding of what? Where are we keeping the rotor? Yes. Rotor circuit. We are giving excitation. Okay. Again, synchronous motor, is it self-starting? No. Synchronous motor is not self-starting because first rotating magnetic field exists. That rotates with certain speed. Physically, rotor has to move along with that speed. No, it cannot happen on its own. We need certain arrangements. Depending on the type, usually laboratory scale, we have induction start synchronous motors, just by use of damper windings. So there are certain arrangements on the rotor sides. Just earlier theory classes, professors discussed that, right? In synchronous motor, they cannot start on its own unless any other external means is provided, right? One way is induction start synchronous rotor. Otherwise, we have some external rotor external pony motor. Pony motor connection and driving. Yes, motors are available, but for our laboratory sake, we use induction start synchronous motor. What it does, we give the supply, RMF is now being established, it will rotate immediately. Rotor also, because of this damper windings, just by the induction motor principle, currents will be induced since they are closed circuits. Now they will get influenced by the rotating magnetic field due to this relative motion force exists between the field and the current carrying conductor. So now rotor starts rotating. Now we need to give the excitation, DC excitation to the rotor once it is reaching near to the synchronous speed. If you have already done this experiment at your institution, you can feel the alignment of the rotor with the stator field. Right? Initially motor starts, but during the synchronization with the RMF, rotor gets aligned, then locked. Now it will again rotate under steady state. During this, at a constant load is separate constant. Say, then usually again this load can be given directly or indirectly. In laboratory experiment, we have that pulley brake arrangement. Pulley brake. Motor load means output is mechanical. How to control that? By belt driven, that shaft drum. That is conventional practice. We used to apply load physically. Indirectly, we can load the motor by connecting a generator at its output. Right? Just like prime mover of the alternator, we are giving as a shunt motor. For shunt motor takes again electric supply. Generator should give supply, but for to give the generator supply, prime mover we are using again electric supply. So it is just for our simplicity's sake. So laboratory, that method also can be followed since it is synchronous motor experiment, as our senior sir once expressed previously in our earlier discussion. While we are applying load to the synchronous motor, because of this what phenomenon? It makes so much of noise, right? It creates so much of troubles handling with that loaded synchronous motors with respect of damping and what do you call that? Hunting. Yes. Because of that, loading of synchronous motor is not smooth. I will show you rotor angle. I got one that simulation kind of experiment. It is available on YouTube. I searched. I will show you how this rotor angle and stator field are getting aligned. What is actually load angle? Physically, that somebody did this. Yesterday, I found this. I have shared in the link also. I will just show you that. So, for the smooth variation of the load, we are connecting at the output of the motor indirectly electrical load of the DC generator. DC generator input is prime mover, mechanical, so we are coupled here. At a constant load of application, if the excitation of the synchronous motor is varying, how the armature current varies, that shows the experiment here. At a particular field current, with minimum armature current, we have unity power factor operation. So it will give us the range of field currents where the armature current operates limited. Except that V curve, if you see minimum point is IA, above and below that point we have increased currents. So we cannot operate that synchronous motor to operate not minimum value, it can be any rated, more than rated values. So by this conduction of this experiment, we will know at what range the motor can be operated, safe range, and what is the optimum value of field excitation such that for minimum armature current, power factor will be unity. Ultimately, system must our objective is to achieve unity power factor, right? By changing this excitation. That is the theory behind this, what we have learned. Yes.
See, I'll just supplement that. See, motor means electrically mechanical. Am I right or not?
Yes.
So now actually instead of the
mechanical load, they are giving a electrical equivalent. It's clear. So what do you mean by that? So this is the motor. Now this is a generator. Understand? So now generator is having a electrical load. So when you start loading electrically, that means what? You need to draw instead of directly having a mechanical load, how you can load it electrically and plot the characteristics. Now coming to this V and inverted V, you see the motor, synchronous motor for a constant load. For a constant load, if the load is remaining constant, so that means you just take input minus losses, this output should be constant. So that means input Vi cos phi, Vi cos phi, so V is 1, I cos phi is 1. So now you vary the excitations. So keeping the voltage constant, when you vary the excitation, what will happen? The power factor will change. The power factor will change from lagging to leading. For over excitation it will be leading, for under excitation it will be lagging. So now the product I cos phi remain constant for a constant load. So that means if cos phi is increasing, I has to decrease. The armature, if power factor is increasing, the armature current has to decrease. So this is nothing but the base is x-axis is nothing but the excitation, the field current. So if one is like this V, other one will be inverted V. at any point you put the vertical line, I cos phi will be the same. Understand? So that is the basic of V and inverted V. Understand? So you keep the load constant, keep the voltage constant. So I cos phi will remain constant. Product of I and cos phi will remain constant. Now by varying the excitations, when you vary the power factor, so definitely the power factor is increasing, current has to decrease, or the power factor is decreasing, current has to increase, because the load is remaining constant, the power drawn from the supply main has to be remain constant. Understand? So that is the basic fundamentals, nothing big in it. So people usually think like what is this? So if you just see the curve, one is under excited, other is over excited, then at the V point you say it is like your unit power factor. So that is how actually is the characteristic. So you tell student like how I cos phi, product of I and cos phi is remaining constant for a particular load. Now varying the excitations makes the power factor to change. So when the power factor changes, if cos phi is increasing, I has to decrease, or cos phi is decreasing, I has to increase. So this is actually you are plotting in the form of a graph, then you are getting V and inverted V cos.
This is some experimental setup I found recently to identify what is physically, what is rotor angle. How rotor is trying to align with the stator magnetic field by producing that counter electromagnetic torque with the load. Right? You observe this. Some laboratory made setup here. He showed it as a sample by enclosing an encoder at its rotor that side, other side, so the speed encoder. Then he programmed it to have a plot between stator magnetic field as well as physical rotor position. Just I have shared this video thing in the group also. Just let us see completely. Then we will come to an idea how rotor angle is now varying with respect to load. If it is subjected to any disturbance or trying to synchronize, play it. See, stator core, in order to show the direction of rotating magnetic field, he made some arrangements of blinking this LED, so they are rotating in clockwise. Play it. You can observe the stator field direction. For indication purpose, he made it stator field red to phasor. In that plot, it is showing the RMF physical rotor position sensor. It is giving the rotor phasor. Now he is trying to slow down the rotor by applying physical force. Trying to slow, not completely. That is now loading. Load. He is trying to slow down. Now rotor definitely cannot always be aligned with stator field. It tries to align, but it will lag. That is where delta comes into picture. Here is the delta. Now he showed that again, revise. Back. One small observation, but yet effective. I found this just last night. I wanted to share, so I am sharing this. See, stator and rotor. See, blue is representing rotor field. He programmed it just to see the physical experiment as well as simulation experiment. He programmed that in MATLAB. Yes. Then he is trying to hold this. Now observe the angle between the rotor as well as stator field.
Increasing.
You are understanding right now?
Then again decrease.
But that means he is changing here pressure. How he is varying now. Physically it is not constant. That is how physically when the load is increasing or decreasing, rotor is subjected to change. Once we know that range, that is why that angle should not be beyond. Can someone recollect, sir? We discussed this, right? This angle between stator. Yeah, what is this?
Stator and rotor.
Stator, no, please. Stator, magnetic field and rotor. Yes. Physically, that angle should not become correct. Stator and rotor magnetic field itself, because they try to align. That angle is delta. Delta should not become
zero.
90.
More than 90. Delta should be 0 and 90. Right. So that is what he is showing. This angle, it should not become more than 90. What it should be 0. Usually it should be 0. Then only P is equal to EV by XS sin delta. Sin 90. What? What?
EV by XS sin delta.
Sin delta.
So delta, when delta is 90 degree, torque is power is maximum.
Maximum power. Okay. If it is beyond 90, unstability region. Okay. That is the observation here. Okay. Next, synchronous motor. We are discussing. Okay, you play this video completely once. That's it. I think you got understood, right? What is the physical significance of load angle? Right?
With variation of the load torque, the load angle changes.
Correct.
Again when left, again it is aligned.
Trying to align it. Because synchronously they have to lock and rotate. That's it. Next. Go to our experiment. So we are inverted yes.
Load angle, torque angle, or the angle between stator axis or rotor axis is the same thing. It is. So when you are, if you go back to those are handling power system, they can easily correlate. Power is equal to between two bus V1, V2 by X sin delta 1, 2. It's clear. This is the angular difference between your say bus 1 to bus 2. So when you are a single machine infinite bus you are taking, it is like reference is delta is equal to 0. Reference frame like infinite bus you are taking delta is equal to 0. Then what is the angle it makes with respect to your infinite bus is nothing but your delta. So what is role? Like if you see the sine curve, sine, so it is like 0 to 90. So that means the angle should be there. So when you are becoming 90 onwards, it's unstable. But during transient stability, those are handling, they will see even if the angle is more than 90, the system is transiently stable. It's clear, transiently stable. So that means if the fault is getting cleared, how to make the machines not losing its synchronisms. Understand? It will come back with the oscillations with the equal area criterion. You would have studied like this basic concept. It's clear. So don't get confused with what is torque angle, rotor angle, or angle between your stator axis or rotor axis. It is the same thing. As you are started loading, he was putting hand. You see the angle was you are applying some brake. So the rotor axis is falling behind the stator axis, but they are magnetically coupled and they are rotating at a constant speed. So that's how the synchronously they are binded and revolving at synchronous speed. So when you say synchronous means what? It's like stator speed and the rotor speed is the same. Slip is nothing but the difference between your stator speed and the rotor speed, ns minus n, that is nothing but the slip. You express in terms of percentage, which is nothing but ns minus n by ns in terms of percentage. So, but in case of your synchronous and induction, you have to tell the concept with a clarity. I will suggest you teach first actually inductions, because inductions, when somebody has studied transformers, you can immediately correlate what is the relation between your transformer and induction. She will say like it is the same transformer with secondary short circuited. You can start from there itself. So then he will come to know what is rotating magnetic field. He will understand. Then he will know slip. So when you come to synchronous speed, you say slip is 0. So then he will understand. Otherwise, if you start here like first synchronous, then inductions, then if you talk slip is 0, he will confuse what do you mean by slip. It's clear. So that is my way of teaching machines, because usually I handle first induction, then synchronous, so that they will understand better. Because if you see synchronous machines, little more more understanding of subject like DC, induction, all these things needed to understand synchronous. So all things you studied, then only you go to BLDC or PMSM motors, special machines. or reluctance motor. Then you understand there actually. See, always we teach in the class actually single phase, though mostly we are using, but we teach them at the end. Why? Because they will understand what is the rotating magnetic field. It's clear. So what is the, see, so far we are talking about like you need 3 phase to have a rotating magnetic field. The flux strength is 1.5 times maximum flux strength. But when you come to single phase, you split the phase by some means. So some means there are so many ways of splitting the phase. Then you are creating an angular difference between two flux. Then only you will be getting a rotating magnetic field. Understand? So when the rotating magnetic field slip over a constant, there is a relative speed difference between a one and others, then only it will experience a torque. So you, when you deliver the lectures, I will suggest like you go through this way so that better clarity of understanding will be there among students. Okay, thank you.
To come first for the students. If you want to teach synchronous machines, you first teach generator. Yes. But induction machine motor. First one. Like what to say? When you teach DC machines, usually first what you read usually the syllabus. First generator, then DC motor. Then we teach actually transformers. Yeah. Because if this is the flow, because so many, though it is distinct, but there is some things, some foundation is required to understand better when you proceed in this. So if you go through some standard textbook, they have written in that manner. So that when you go in that flow, you will see they would have started the single phase induction motor the first. Why it is last? The special machine is again last. So this is the things.
As we are discussing the experimental procedure of this conducting synchronous motor to find the characteristics, right, between the PG excitation and the armature current as well as power factor caused by it. Usually, if this experiment is conducted physically, then a lot of things to get to know how the synchronizing happens. During the synchronization, what care to be taken, right? But anyhow, we'll assume that those all necessary conditions are taken care of. Then, how to make familiar student to conduct this experiment without having any difficulty. Synchronous motor, we need to give first AC supply. This is synchronous motor model. The circuit diagram. Okay, synchronous motor, 3-phase supply here is given. Okay. Directly can we give? We can give, but it is not suggested. In case of induction motor, we should not give. Induction motor self-starting. 3-phase induction motors are self-starting, but we need first reduce the current. Directly, if you close this switch at 400 volts at 5 hours, these things, that is practically not suggestible. Safety first ensured. But for a 3-phase induction motor, start required compulsory, because motor itself is now causing in DC motors also we have started. Right, as sir previously.
See, another thing, when you are in the laboratory, actually, you might have those are already handling. See, synchronous motor. How do you start actually? Usually we start in the induction principle with the help of damper winding. It will start as an induction motor. Then you give the excitations, DC excitation. So when you give the DC excitation, you will feel the jerk. When you give the DC excitation, you will give the jerk. Then you will see your rotor axis and the stator axis get magnetically coupled. Then they rotate at a particular speed. That is the synchronous speed. So only if you do it physically, you will know how it is started as a inductions, but when you give excitations, how it is becoming synchronous. Yeah, some smoothness will come, so you can see. But that jerk, you have to tell the student, like you see the jerk, and see the speedometer and the current resistance variations. Then you go to finally this V and the inverted V curve characteristic.
Here we are connecting two wattmeter to that two wattmeters. We are connecting two wattmeter. Actually, whenever we are just increasing the field current,
No, this 2 watt meter is like for a 3-phase power measurement.
also we are calculating power factor.
Yes.
So for that power factor, we need 2 wattmeter, 2 wattmeter. Okay, so whenever we are operating this one, actually, what happens initially the 1 wattmeter is increasing.
Yes.
Otherwise it is decreasing.
Decreasing.
But after some time,
After sometimes it will get here. Then you have to reverse it. Either the current coil or the voltage coil you have to reverse.
and
Hi. You are coming to this point. So this point will you have to change because then only because it is the excitation is varying.
protected. Because, why? Because whenever we are increasing, wattmeter is increasing, whenever at some field current, it is decreasing below zero. So at that time, we have to reverse the MNC.
Current coil, preferably current coil.
What value are you giving the expected scatter? Are you giving the supply at this rated value or using the starting? It's
No.
stator supply. What value are you giving directly for 15 volt light voltage or whatever the rated voltage? Directly you are giving, or like this you are using an auto transformer and then you are
Not
you didn't have an auto transformer. So that's why I'm going to tell the same thing here. This is induction start, right? Induction start, which initially we can assume this as induction motor. Induction motor needs us, but initial starter. Assume a auto transformer starter.
I think slowly we are increasing the field current. Slowly,
When the machine is operating at
rated
rated
current, we are slowly increasing the field current.
yeah.
At that time, what happens? Initially, one was decreasing, another was increasing.
Yes.
Whenever it is going below zero, so at that time, live we are just changing the position. So that is not it can create problem.
Not problem. You have to do it because you see because total power consumption is nothing but W1 plus W2. At some point it is zero. That means it's a negative. Like so, you have to calculate because the power factor decides what will be the reading of the watt meters. So power factor depends upon the excitations. You are varying the excitation, keeping the load constant. So when which one? Why suck? There will be. This is the where there will be a pin. This pin. So you just remove it. Just put it. That's all.
Again, we have to off the supply.
No need of off. No need of off. See, if you are not doing a naked wire. See, there will be a wire and there will be that U pin.
Not pin. We are not using pin. We are using.
You have to off it. This set of reading. Discontinuity again. This set of reading. So it will come like this. So you have to 2 times. You have to do it. But if you are this is like this comes U type of thing. So you can take it out. That's why the U is here. So you take it out. Then just reverse it. Then put it. Because this side is the plastic. This side is plastic. But if that is not there, then it will not stick to your knob. So you have to put it in the finger. And no other option. So you have to switch off and come. You will not get this V. You will get this part. This V part will not there. Again, you will get this part. What is this? So you have to draw approximate this part only. But if you are really doing, you will see like each part. No, you are keeping the, you know the how much load you have given, no? You have not, you have given the load is constant, no? Only the, you are varying the excitations, DC excitations. DC excitation, how do you vary it? Through the rheostat only you vary it. Understand? So you vary, you know this, up to this point it will come, then wattmeter will read negative after this. So you keep here, connect it, then you vary here, then it will go the other side. So the extra precaution you have to take.
Previously, one more thing also, raised such a same question. In industry, how these open circuit test and short circuit test with such larger value. I enjoyed after that session. They do it. They do it really with high voltages, even at industrial level also, with the short circuiting also, and the complete loading also by having larger values of load banks. They do it, but provided not just like negatively what we are doing at like number, even at the moisture, even at the air content, even at the vibrations, everything they are going to take care of, and with the high rated measuring instruments, with all precautions taken care, turbines at the power plant, they run at rated speed, then they generate voltage, they increase the exciter. This is a shunt generator, exciter usually used it, and they do the test, insulation test, everything they have. In our research laboratory also we can have that 1500 ampere clamp meter to see the power quality experiment. Analyzer, power quality analyzer, we have 1500 amp, means 1 kilo ampere, which is very high in electric. So they do it practically. But by taking all measures into taken care of, they practically do it. So after the synchronous motor is given supply by this induction motor start. So still we are employing here for the same operation and auto transformer starting. Right? So from here we gave the supply so that RMF is produced here. Now initially motor runs that. We did this because it takes lot of time, one by one steps to be calculated. I just wanted to demonstrate. Just before only we conducted this, we am now showing. It is not synchronous speed as per the nameplate details. It is less than this 1400 something. Then what to do? First supply is given for synchronous motor. Still the motor is not running under synchronous speed. Rotor must be excited by this DC supply rated voltage. Then as now we are discussing. Once the supply is given, when the rotor is aligned with the synchronous rotating magnetic field, it will show the data. Now what to do? Apply some load to the motor. Indirect load DC generator he has taken. Simple way. Okay, some load is applied. Values are noted down. Now what should we observe? We should observe the change of armature current with respect to the field and power factor also simultaneously, so that we will get to know the range. At what ranges we can operate this synchronous motor, and at the minimum value of armature current, maximum value of power factor is practically how it is varying. For one load we tested now. Okay, we took the graph. Okay, how to do that in this particular platform, virtual lab. Okay, after connecting this, closing this, okay, we varied this as per the procedure we follow. After that, connected the DC supply. Then check the speed here first. These are the sequence of steps should be followed while conducting the experiment. Then after, apply the load. Then take down the readings one by one between the field current as well as armature current. What is field current here? In this entire setup, what reading should be on X axis? In this, which meter? This is the field current. Yes, next, armature current. What is armature current to take on y-axis here? This is the. He has named them here. Right. You can observe from here, ammeter is connected from there. After one by one, reading, okay, start storing the data. One reading, change there, start storing the data. show the data one by one, the reading gets noted. If we observe the readings here, at all values of excitation, we observe 1500. Practically also we will observe the same. In synchronous motor, speed all is constant. Right, we will get this constant speed even in the during physical experiment also. Then input voltage is constant, okay, IFS to IAL, observe this, and power factor also. Okay, power factor plus lesser, next unity. From here to here, what is this region?
Lagging load.
Again, lagging or leading. This is synchronous motor. Again, from here to here, again it is decreasing. Middle one is unity. You take left side is what and right side is what?
Lagging, that is the leading.
For what? Left side is lagging for synchronous generator or synchronous motor?
Because generator.
Lagging motor.
And leading for
So, okay, after plotting this, we got this I think, right? Okay, IA. Okay, this is IA and this is okay, we got this is unity power factor. What is this region and what is this region? Correct. Thereby we should derive this. Overexcited synchronous motor is leading power factor region or
Overexcited is leading, underexcited
for synchronous motor. Correct. And reverse for generator. So based on that, below this, it is overexcited or underexcited. Just have to try to see what is this region and this region.
Underexcited. That.
Left side is
Underexcited. Under. Because field current is less.
right side is
Overexcited.
then left side is what power. This is synchronous motor. I just want to see lagging, leading, unity. Unity is clear. One.
That side lagging, this side leading.
Power factor.
opposite na rapid lagging. Inverted.
This is inverted. Power factor is now power factor. It is coming towards this. One after this it is decreasing. Okay. I think we have given that question in the quiz time. Let us see. Please answer those questions. We have given as a quiz in the Google form. Link has been shared already. Anyway, you show the power factor. IFS versus is it this? Generator. Mistakes may be there.
No, actually we changed the loads. That is why
At constant load, if you take precise readings, then if you carefully do the experiment, accurately we will get the graph. So that is how we will get understood of the theoretical knowledge applied to the experimental setup in the laboratory. We have one more experiment also I wanted to show. Sequence impedance components of synchronous generator. In power system, we have symmetrical components. I think most of you are from power systems background itself, but I am not from the power system. I am from power electronics specialization. Anyway, in the alternators first, it is primarily used for the fault analysis. We have a balanced fault, unbalanced faults, line to ground, double line, ground, triple line, etc. Okay. When these faults are occurring, how much is the impedance offered by the alternator? Okay. That analysis is required to determine the reactance, to get the knowledge of the reactance under fault conditions. Fault can happen within a momentary interval of time, right?
Zero impedance because high current is flowing.
We'll discuss. In 10 minutes I am going to discuss the same. Positives, we have the symmetrical components out of which we can see for the parameters, say currents here, positive sequence, negative sequence and zero sequence. Positive sequence means under balanced condition, whatever the currents are flowing in clockwise direction, say that is positive sequence. Otherwise uniform rotation, ABC sequence, RYB sequence, in which we are taking that currents observed during that normal condition. If short circuit happens, then if a fault happens, then how much is this alternator providing the reactance? We have subtransient reactance and transient reactance. Once the fault is clear, what do we get? Synchronous reactance. Say impedance we are talking, but if the armature resistances are say completely negligible, then if we neglect reactances, we are finding. Subtransient reactances, when we are dealing, so that it does not last for a longer time. Usually, say 4 to 6 cycles, we get that subtransient reactance, but balanced fault, that is sinusoidal only, right? Then after transient reactance, it is varying up to 6 cycles to say 5 seconds, etc. Otherwise, less than very short interval of time. After that, during this time, if the fault is clear, then we will go for that synchronous reactance remained, right? It is mainly required. That experiment is also there for finding the reactance parameters of an alternator. Positive sequence, negative sequence and zero sequence. Positive sequence are those during we got this short circuit test, open circuit test. Short circuit test we are doing, right? That is nothing but a fault. Short circuit test, we can treat that as a fault, right? We provided short circuit current will not go beyond its rated armature current. Okay, we can, that is fault current because we are shorting. So one impedance we are getting that synchronous, say XS. Then after negative sequence occurs whenever unbalanced faults occur. Unbalanced faults occur, those currents we are now theoretically analyzing using this negative sequence. Zero sequence. What is this zero sequence? Zero sequence currents occur when the currents flows through neutral. Ideally, VA, VR, VY, VB phasor sum must be zero if that system is balanced. Right, Vm sin omega t minus 120 minus 240, yes, they give neutral. But if such fault occurs, if current is flowing through neutral, we need to see how much neutral current that this alternator can provide with what impedance. So that is the experiment. It is showing the sequence operations. These to find the sequence parameters. One more experiment is next order induction motor experiment, speed control, finding the equivalent parameters. I think we discussed equivalent circuit of 3-phase induction motor. We get no load component. It is just like single phase transformer, per phase equivalent of transformer circuit. What do we get? Primary side. First, stator resistance, stator leakage reactance, magnetizing component, magnetizing reactance, and core loss component, core loss, energy loss component per phase. Then rotor side, we have rotor resistance R2 and X2. In case of wound rotor, we have rotor leakage reactance. In order to model the mechanical load into the electrical parameter, we use the term called slip during running and during starting. During standstill condition, we have two equivalent circuits, right? But usually we employ under running condition. During running, what would be the equivalent circuit? SE2. Rotor is now receiving that slip times standstill induced EMF, then R2, X2. Mechanical load we want to represent in electrical equivalent. If we take S common here, E2, R2 by S plus X2, R2 by S minus R2 plus R2, say. Then plus R2 plus X2, rotor side parameters, R2 by S into 1 minus S, that equivalent circuit of induction motor I am speaking about. Thereby we see by varying the speed, how the torque speed characteristic, efficiency, circuit diagram, that test, what tests are required to get those equivalent circuit parameters. That experiment is there in induction motors. Alright. So what parameter? Xn, we need to find the magnetizing reactance component, and by using no load test and blocked rotor test, those tests we are doing for the induction motor case, right? And thereby we calculate the other parameters. Next, single phase induction motor equivalent circuit again. Three phase induction motor principle is separate. Single phase induction motor working is separate. Here, single phase induction motors are not self-starting. If you observe, we make them rotate by means of splitting the phase. By means of splitting, we have such experiments also here. Three phase alternator. Okay, that is okay. We can note no load test, block rotor test, three phase induction motor. Usually it is given, but different colleges may have different setups for that. But under VPUT we got this no load test and the block rotor test together, and to find the parameter, we can find the equivalent parameters, as well as we can plot the efficiency characteristics, and whatever we for a slip ring induction motor, we can find this variation of this, how maximum torque, starting torque, resistance control, that can also be done. And one more experiment is also there that I cannot show at this point. Speed control of induction motors by variable frequency drive. That is actually point of interest. Research. We include power electronics based motor control. Together they form drive. Right. Speed control of induction motor using variable frequency drives. Achha, can I have a quick answer for that variable frequency? Entire electrical engineering we are discussing to keep the frequency constant. Okay, but our requirement is to control the motor by say variable frequency, and V by F we are taking. Okay, in what thing can make the frequency change? So I'm just asking how we change the frequency. Yes, from a fixed frequency to variable frequency. Who can do this?
Inverter.
Yes. We earlier we have that converter named called cyclo converter, frequency changer. We get that, right? And for voltage control, we have single phase and three phase voltage regulator. And for DC to AC, inverter. AC to DC rectifier. Right. One of the experiment listed in there also. So no load test on we see some this power virtual power. Provided those machines are well established, then I would have taken you there also. As we are newly developing, soon we are expecting. So that is why I am just giving a brief view to best of my possibility. In that virtual lab itself. Virtual lab. Last me, I request all of you, those who are not aware of this or not well familiar by now, at least try to do simulations by this virtual lab first, then try your respective laboratories, then you verify how far these are similar or related. This is developed by IIT during our Corona period.
Some by IIT, some by
they contributed. But as I am saying, IIT don't take them granted.
IIT Kharagpur has developed high voltage lab. This is how it will work. Virtual lab, first high voltage lab, because high voltage lab is very costly. So that means free of virtual lab. Then we actually they felt this is more useful. So now they have brought everything into a single platform. So they have given project to IIT Delhi, IIT Roorkee, in this Deep Royal, and even new IIT has come. Even other virtual lab you can see from College of Engineering Pune. Even Amrita University, they have their own virtual lab. So they have gone into every branch of engineering, not only electrical. So this is a platform, single platform. You will get so many varieties of things. So now, because this Deendayal, this university, if you see, they have taken some video type, very, what to say, very old fashion. But they have developed a long back, but at least they have done in those days something. So now if you see new IIT, they are coming with more, what to say, more user friendly. Students are attracted to do, and they can try different options and see how the graph is being plotted. So you explore here. Even if you have a like actual lab, still you use, I will say, you use this platform for every subject, every subject.
Students are getting so interested about the physical.
No, that is there. So now when you show it, maybe in a theory class you can show, or you see here first you, because the 3-hour lab, give 1 hour instruction and about this, show them, so they will explore, because those are slow learner. Your next class we are going back to next experiment. So they will say, भाई थोड़ा उधर देखो, थोड़ा तुम्हारा clarity आएगा. So even sometimes you will see the theory will be more like you get clarity when you go through the experiment and do by yourself. Because many times what in the lab, either lab assistant do or we do, they will just see, and 1 or 2 students will be active, other 3 students they will just copy. So they just copy and लिखो report लिखो, काम खत्म. तो दिमाग में उतना जाता नहीं मेरे को जो अनुभव. So you tell them, भाई देखो शाम में इतना YouTube देखते हो, भाई ये तो YouTube जैसा है, करो थोड़ा. So you, not only machines, all subjects, even power electronics is also very good. When you go through this load flow analysis they have done now, very nice. Just you put click, you will get the result. At least तो उनका दिमाग में आएगा कि क्या है PV bus, क्या PQ bus, how to select, you do this something result. Then you verify with the what you are getting in the book, Hadisadad, the same thing you are doing it here itself. So that some year, because the writing code nowadays, students, they are smart of course. Now they will ChatGPT will write the Gauss-Seidel method, so you can do it. Otherwise, your PhD will get over. You cannot write the Gauss-Seidel even. Understand? You forget about Newton options. So that is the things. That is the challenges. Understand? So the real challenges. What is my experience during MTech? I am telling. One of my friend, he will sit continuously 48 hours, 72 hours he sat and he finished Gauss-Seidel, Newton-Raphson, the first decomposition when we are doing MTech. So some people are there, so they know they have that juice. So everybody cannot do it. So that's why commercial packages came to market like My Power, ETAP. That is there. So with machines also, so many things are, have come, but I doubt whether those things are available in our Odisha. But if you see, go to VIT, SRM, they have purchased because they have money, so they are investing so much. But at least this virtual platform is a like boom, like we can use free of cost. Right?
Some number 999 so made for students. But you will also share the news so that you can.
Some which session Google links.
You put any number you put. 1, 2, 3, 4, 5 you put.
We have shared a link, two links in the group. Kindly fill out that two links. Two links, sir. How many? One or two links. Kindly fill out. Break. Certificates are under editing process. We are going to get the certificate. We will take a break along with this test break. Right. As soon as you finish, you will continue. Vice Chancellor sir is about to come now. So as soon as he comes, we will wind up. You can close our session by validating. So we'll take a break as well as session together.
So registration number.
1, 2, 3, 4, 5.
Both. You have to fill the both. Fill the both. Fill both the form. Then after we will the break.